This is video 17 in the series of reinforced concrete slabs. This video will deal with the plastic analysis of slabs, and it will explain you how to create yield lines or how to draw yield lines. The method of yield lines was first introduced by Johansen in 1950, and later on it was picked up in 2003 by Kennedy and Goodchild. A lot of formulas and elements in this video will comes from the reference of Kennedy and Goodchild. Take on the y-axis the load and increase it from 0 to a certain value. On the x-axis you put the deflection of the middle of a slab loaded by uniform distributed load. When the applied load is small, then you will have a linear relationship between load and deflection. Then the first cracks appear in the slab without a significant increase in the load, and this zone we call the elastic behavior of the slab. After the first crack there will be a crack redistribution, and in this zone we call it the crack zone or the cracking zone. Notice that in the second zone the slope between load and deflection is much fainter than the slope in the elastic behavior. So the modulus of elasticity is smaller, up to 1/3 of the modulus of elasticity of uncracked concrete. After that, you get a plastic deformation of steel until a point where there is a rupture and where the load cannot be increased. A part of the elastic behavior and the cracking zone, this is the zone where the load is the surface load of the slab. A graph like that is a load deformation diagram of a reinforced concrete slab, and you see that this is different from a beam because now the moment redistribution capacity of a slab is very high. So in a slab you can have first development of some cracks, but then the zone next to it will crack and the zone next to it and so on. So you will have always a momentary distribution in the slab. The zone of plastic deformation of steel, that's yielding of the steel. From that point on the steel is yielding. And the rupture occurs when the concrete, of course, is crushed, when the compression force of the concrete cannot take it anymore. A yield line is the collection of points along which plastic rotation occurs. You can say that a yield line is in fact more or less a crack pattern after moment redistribution. But there are conditions. At the ultimate load, the steel must first yield. So the compression in the concrete must always be smaller than the FCD. So first the steel must yield and the rupture must occur while the concrete is crushed. The consequence of that is that you cannot have over-reinforced sections. Concrete slabs with too much reinforcement in it, the yield lines will not develop as you wish. The concrete will first crush and the slab will not hold. This means, in fact, that you should use the method of yield lines only when the effective depth of the slab is less or equal to the optimum effective depth of the slab. Optimum means the maximum use of strain of steel and concrete. Also, a consequence of is that you have ductility restrictions are needed because the different parts of the slab along the yield lines, they must be able to rotate, and otherwise you do not have a momentary distribution. So the ductility restrictions are needed, and ductility is in fact the extent to which a material allows plastic deformation. So yield lines you can only apply in not over-reinforced sections and where ductility is guaranteed. The definition of the plastic bending moment, MPD, of a slab is given by the reinforcement per meter width of slab times the yield stress of the steel and times the lever arm, which is by default 0.9 times the effective depth of the slab. This definition makes it easy. When we can calculate the plastic bending moment in a slab, you can calculate immediately in a very simple way the needed reinforcement. So you don't need concrete tables or anything like that. Take care. Yield lines, it's about a plastic hinge. It means that at the origin of the yield line, that the bending moment is equal to the plastic bending moment. It is not a mechanical hinge, because for a mechanical hinge, the bending moment is 0. So don't make that mistake. So plastic hinges, the bending moment is equal to the plastic bending moment. It has been extensively tested. This is a slab and it's loaded by 8.2 kilonewton per square meter, and you see here the crack formation on the bottom of the slab. Then you increase gradually the load and you will see that a pattern of cracks is developing, and at the end you will see clearly that you have this kind of crack pattern that is in the rectangular slab. Some rules to create or to estimate where the yield lines are. A yield line is a straight line. This is an assumption, but it fits more or less the reality. Yield lines, they lie along lines of support. They pass over columns. They pass through the point of intersection of the axis of rotation, and they end at the slab boundary. Just take care that once you have drawn all yield lines, that the different slab subregions must be connected by a failure mechanism. Let's put that in practice. A rectangular slab on all sides simply supported. Now we will first mark the axis of rotation, which is at the support. And then we have some auxiliary lines. The auxiliary line goes into the bisector of the corners when the corners are both of the same condition. So you have 4 same corners, it's 4 times the bisector of it. Then you draw, when 2 auxiliary lines comes together, you draw between them another auxiliary line, or you can say that the axis of rotation, which are horizontal, they have an intersection on infinity. So this, in fact, this blue line is the bisector of the 2 horizontal axes of rotation. Then you can draw the yield lines, and this is the yield line pattern of a rectangular slab, simply supported on all sides and loaded with a uniform distributed load. This is exactly the same kind of pattern that we saw in the test with the slab that was loaded gradually more and more. There are some rules, the 30, 45, 60 degree rule, when there is simply supported edge coming together with the fixed edge or clamped edge. When this occurs, then the angle will be 30 degrees and 60 degrees, like it's mentioned here on the drawing. When those two conditions are the same, for instance, they are both are hinged, then it's the bisector of it, so it means it's 45 degrees. Here again, you have hinged, clamped, so it means 30 at the side of the hinged and 60 at the side of the clamp. And when it's the same, then it's again 45 degrees. This we call the 30, 45, 60 degree rule. Now, this rule is only valid if the sum of all angles in the same corner equals 90 degrees. For instance, let's take a balcony, and this balcony is clamped on two sides and simply supported on this side because it's, for instance, then the yield lines will be here for the hogging bending moment. There is one yield line here, one yield line there, and then because of symmetry, we can take the bisector, no problem at this moment, because it's a symmetric situation. Normally this rule is not valid. You see that this corner is somewhere between 60 and 90 degrees or something like that, but because of symmetry, you can easily say this is the bisector. On the other hand, on the other side, you don't know where this yield line is situated. You don't know the angle alpha because the sum is it's more than 90 degrees. Another example is a slab with a formation like it is drawn up here. One side is hinged, the other side is hinged. All sides are all three sides are hinged, and the other one is clamped, and this is free. This is a free end. How can we draw now the yield lines? Well, we start in a corner that we know. This is hinged, so 45 degrees. That the yield line must be situated like here. The other side also symmetrical. So it's 45 degrees. The yield line runs like that. Then the corner, the bottom right, it's clamped. So it's 60 degrees, hinged 30 degrees. So the yield line is somewhere like this, and they join together in that point. Then you have the horizontal joining in that point. But now, where is the yield line joining for this corner? Well, we can solve that by using fictive points of support. We just continue this as clamped support, the other as fixed support. We know now this is 60 degrees and this is 30. We draw the yield line, but we stop at the end of the slab. So now this is the pattern of the yield lines. Another example, for instance, you have a kind of a balcony, which is a slab on three sides. It is hinged, and the other side it's free. It's a free edge. We draw the axis of rotation. We draw the auxiliary lines, and then we start drawing the yield lines. Making this a yield line is not possible because if you do that, you do not have a mechanism. That's why the last rule, remember, of yield lines, you always need a mechanism so that the different subregions can rotate. Okay, so this is now the yield lines for this type of slab. Now we can have a small balcony, for instance. It's hinged on the three sides, and this is free. Then we'll do the same exercise. We take the rotation axis. It will be like that. Then we take the auxiliary lines, the blue lines. And now we take the yield lines. And you see that this is slightly different pattern because this is outside. If I draw a yield line like this, I can put an auxiliary line like that, and then you can put here a yield line, then you do not have a mechanism. So this cannot be there. Now, take those two types of balcony. If B is smaller than 2A, then you have a type of yield lines like this. And if B is bigger than 2A, then you have a system like it's shown here. You can also have a combination of columns and continuous support. We start with the axis of rotation. Now there's also a rotation axis through the column, but we don't know the direction. This can go in any direction. We don't know. We must have a mechanism, so at least we know it's something. It can be like that, or it can be horizontal or vertical, or everything in between. In this case, because of symmetry, we can easily make the assumption that this is 45 degrees. Later on, we will see how we can calculate this angle by means of optimization. This is now, we take it from symmetry, this is 45 degrees. We take the auxiliary lines and take the bisector. And now we can draw the yield lines. You see that this is, for instance, how the loads are transferred. This portion of the slab is transferred to the column. This portion is transferred to this continuous support, and this portion of the load is transferred to this portion. We can take another example. We take the axis of rotation, the auxiliary lines, and again we can draw the yield lines of that slab. And then you know that this side is taking this load and this side is taking that load. We can also have two column supports and one line continuous supported. We take the axis of rotation. Again, this angle should be optimized, but because of symmetry, we can easily take it as 45 degrees. We have the auxiliary lines and the yield lines, and this is the yield pattern. Then we have a corner of a building, auxiliary line, the axis of rotation. The auxiliary line is just the bisector of the corner, and then the yield line. You only have one yield line, which is here. If this, when this slab is fixed against the walls here, and it's fixed, then of course there will be a yield line running from there to there, and a yield line running from there to there. And the most general case of a flat slab, for instance, you have a piece of slab, any shape, on three columns, for instance. Then you draw axis of rotation. Again, you don't know the angle, but we assume, and we make sure that all regions, subregions of the slab forms a mechanism. Then we draw the auxiliary lines, and then you can draw the yield lines for for a flat slab. Suppose we have a circular slab, and it's continuously supported around its edges. Then the axis of rotation, well, in each point of the circumference of the circle, there is an axis of rotation. In each point. I only draw a very few, but in fact it's in each point. Then we draw the auxiliary lines. They go from this point to this point, and so on. But there are many auxiliary lines, infinity in fact. Then we draw the yield lines, which are of course this. This pattern we call the fan. So in fact there are a large number of yield lines like that. I only drew a couple of them.